In this section, we'll talk about how system inertia is estimated, to go through a few of the different techniques and methods for estimating inertia. It should be noted that system inertia is not actually measured directly, but is estimated from measurements of frequency and power, etc. A fairly obvious way of estimating system inertia is to count up all of the known inertial contributions from synchronous generators and condensers in the system. And usually this is typically counting up all the large machines that are in the system, where you know what the inertial contribution is in megawatt seconds, or you can estimate roughly what the inertia constant for each generator is, depending on technology type, and you know their rating. So you just sort of simply add them all up. But this method really can only set the lower bound for total system inertia, because it doesn't include the inertia from smaller distribution connected or embedded generators, and it doesn't include the inertia from synchronous motor loads. So all of that is neglected and they're difficult to find. And the sort of contribution from these demand side inertia and small distribution connected generators is quite large in different systems. So here are some estimates for the portion of demand side inertia or uncountable inertia to the total system inertia. In Great Britain, it was somewhere between 17 and 25% of total inertia. In Ireland, it was between 2 and 17%. And in the Swiss, we've seen it to be between 20 and 30%. So these are material contributions, and they change across the day, and they change depending on load. And so if you're looking at inertia estimates and in its totality, they should probably be counted. Therefore, if you want the total system inertia, including the load or demand side inertia, then you need to make estimates based on some kind of measurement. And so most estimation methods use a linearized representation of the swing equation. And pretty much all the ones that I've seen in my experience use this kind of a swing equation based estimate as its basis. And what you're doing is you're taking usually frequency traces and you calculate the Rockoff, so some estimate of the Rockoff at the point of a disturbance. So this is t equals 0. And of the disturbance, you know what the active power of that disturbance is, and then so that you can work backwards and you can calculate the kinetic energy or the inertia. However, there's some key assumptions here, because you can see that this doesn't use all parts of the swing equation. So the first assumption is that the disturbance is actually instantaneous. So this needs to be a generator trip or a large load trip. You can't have it sliding or ramping down, and this is no longer valid because you'll have other effects of like primary frequency response and load relief effects coming into play. Secondly, the system frequency, and by extension the first derivative, the Rockoff, has to be able to be measured accurately and at high temporal resolution. So usually a SCADA trace is not good enough, like a 4-second or a 5-second SCADA trace. You really need something with very high resolution, sort of in the 100 millisecond or even lower resolution scale. Thirdly, the onset of the disturbance has to be accurately determined, because you're actually evaluating the Rockoff at the onset of the disturbance, so you need to know when that is. And that's not as easy as it sounds, and we'll go into some of the issues around that. And lastly, we are neglecting the effects of load relief and any primary frequency response. And so this method is really only valid for a short period after the onset of the contingency. So you can't keep using this method 4, 5, 6, 7 seconds into a contingency, because it no longer is valid when you have the effects of load relief as well as primary frequency response coming into play. And this method becomes even more difficult if you have fast frequency responses coming in. The first complication in estimating inertia is actually the measurement of power system frequency. So frequency in an AC power system is actually not directly measured at all. And so it's also another estimate. And it's an estimate based on voltage and current measurements. And there's quite a few methods for measuring frequency, but here are two common methods. So the first one, in the zero crossing method, is quite simple, and it's intuitive, and it's really based on the idea that there are actually two zero crossings in every sinusoidal waveform period. So you're basically just counting pairs of zero crossings, and you're dividing that by some kind of observation window, and that should give you your frequency. A second method is based on the idea of a phase lock loop, and it's basically calculating the time derivative of the voltage phase angle. So if you have a phase lock loop and you have a measurement of phase, then you can use that phase to then calculate your frequency. These frequency measurement methods are perfectly fine when you have pure sinusoidal waveforms for voltage and current, but unfortunately that's not often the case in real life. And when you measure the raw voltage and the current signal, it can be distorted. So it can be distorted just by the transducers themselves through noise, and it can be distorted by harmonics, also by voltage dips and from faults, and also from phase jumps. So here are some errors that can occur when using the zero crossing method on a distorted signal. So in this case, some noise and harmonics. And you can see when you're counting up zero crossings, where you have lots of noise, you have lots of zero crossings. So your frequency will be a mess in this case. And when you have voltage dips and phase jumps due to a short circuit, you can have this kind of distorted waveform. And this is a kind of waveform that PLL type frequency measurements really struggle with. And so what you might end up happening is when you get your measured frequency shows transients. And you see this is an unfiltered measured frequency from an actual fault in Great Britain. And you can see that the transients are quite large, and usually you'll need to do some kind of filtering to clean up the frequency measurement. Another complication in the measurement of system frequency is the assumption that frequency is the same everywhere in the power system. And that doesn't hold all the time in real power systems, particularly when there are clusters of generators in geographically dispersed locations that swing against each other. And so they lead to sort of inter-area frequency oscillations that are caused by the exchange of synchronizing power. So this is really more common in systems that are not actually strongly meshed together, and with generation clusters are only weakly linked. So looking at sort of cross-border interconnectors between countries, or even between states in a single country. Got a couple of examples here. The first one's from the Nordic system, which comprises Norway, Sweden, Finland, and Denmark. And here we can see that the frequency measurement in Finland and then in Denmark, which are two fairly geographically dispersed locations, is oscillating against each other. And you can see here that Finland is in blue and the Denmark one is in orange, and they oscillate against some kind of system frequency trace. And this is after a 580 megawatt generator contingency. A second example is from Great Britain, and so here we can see the frequency trace from an interconnect trip in the southeast. I believe there was an interconnector to the Netherlands, and here we can see that in 3 frequency measurement locations, one in the southeast, one in the middle of Great Britain, and one up in Scotland, you can see that the frequency is not the same, and actually there are some oscillations around a sort of average trace here as well. And a final example is from the Australian net, and we can see here a frequency trace after a contingency where a lightning strike struck the QNI, which is the Queensland New South Wales interconnector, and separated Queensland from New South Wales, and then later South Australia also separated from the rest of the NEM. And you can see here you have a frequency measurement in South Australia, frequency measurement in New South Wales, and one in Queensland. And after the separation event, you can obviously the Queensland one's going to go off on its own, but you see here that between New South Wales and South Australia, you can see some oscillations in the frequency trace. Because of these locational variations in frequency measurement, rather than selecting a single location to measure frequency, a system frequency can be calculated by taking a weighted sum of frequency measurements at each generator location. So these are weighted by the generator inertia constant, and this is called the center of inertia frequency. So you take the frequency traces and then you just weight them by the constant h. And here is an example of the center of inertia frequency in the Swiss, as well as the Rockoff. You can see all the frequencies here, and then the center of inertia is somewhere in the middle there, like an averaged out frequency trace. The Swiss is probably not a particularly great example for the center of inertia frequency, because the Swiss is quite compact and mesh and don't tend to have too many oscillations in the frequency traces, except for some small generators that are a long way away, which are these ones here. You can see here Parkston, and this is the wind farm, Colgar. Wide area measurement systems, or WAMs, for example, using phasor measurement units, PMUs, they can be used to measure frequency in real time, and they're time synchronized at all different locations in the power system, and as an alternative to the center of inertia frequency, where we're weighting against the generator inertia constants, what we can do is we can sort of create an average system frequency trace using different PMUs, not necessarily at different generator locations, but anywhere in the network, and we can weight them using a generalized weighting function. This is like the average frequency trace with these generalized weights, and you can choose the weights if you know the sort of the distribution of inertia in the area around the measurement location, or you can just weight them all equally. So this is some PMU based measurements from the University of Tennessee. They've got this thing called FNet gridiron, which measures frequency all around the US. In fact, they've got them all around the world, and there's one in Perth as well. And you can see here that with the GridEye, they've got them all over the US, and you can calculate the frequency all around the continental US. We just spent the previous couple of slides talking about all the problems with measuring frequency, but for inertia estimate, we actually need the first derivative of frequency, which is the Rockoff. And the inertia estimate is actually very sensitive to the measured Rockoff. But because Rockoff is measured from the frequency, sample by sample measurement of the Rockoff, which is you just take the delta F divided by the delta T of each sample, is also very sensitive to the quality of the frequency measurement. And so when we have all these effects that we were talking about before, with all the noise, the transients, the oscillations, and so forth, they can have a very material impact on the measured Rockoff. So there are a couple of methods that are being proposed in the literature and used practically as well to mitigate these issues. So the first one, which I'll talk about, is an averaging window. So this is used quite often in Northern Europe and Great Britain, and basically the Rockoff is calculated by taking the sample by sample Rockoff measures and then putting that through a sliding averaging window. So 500 milliseconds is common in Europe. So basically you're just taking this point and this point, and that's your Rockoff over 500 milliseconds. Here is this diagram showing that if you took this point and this point, which was 100 milliseconds, you just get a huge Rockoff because of these oscillations that are occurring, possibly due to a fault. But one thing to note is that the larger the window, the less accurate this Rockoff measurement is, because of the effects of primary frequency response and load damping effects, so as we mentioned earlier. A alternative option is to use a polynomial fit to the frequency trace. So rather than taking an averaging window, what we do is we try and fit a polynomial to this sort of frequency trace. Here you've got some oscillations in the frequency trace and you're trying to fit a polynomial to that trace. And Inui, who sort of proposed this back in the 90s, he was looking at the Japanese system, and there were quite a lot of oscillations between two regions, and he found that a fifth order polynomial fit worked pretty well. However, Ashton, in one of his papers, when he was looking at this in Great Britain, he found that the polynomial fit was adversely influenced by frequency effects outside of the inertial window. So this would be the inertial window, and he's finding that in Great Britain that when you fit the curve over a longer period of time, the curve is very influenced by things 10 to 20 seconds out. So yeah, the jury's out in terms of whether or not the polynomial fit is a good option or the averaging window. A final complication I'll discuss in calculating the inertia estimate is determining the onset of the disturbance, because you need to calculate the Rockoff and you need to evaluate it at the onset of the disturbance. So there are several methods for determining the disturbance start time, and I'll go through a couple. The first one is a manual method. So this is very easy, and the start time is manually selected by inspection from the frequency trace. So you can see here, this is a frequency trace, and here's the disturbance. By inspection, you can say, okay, yep, it starts here and here minus 0.6 seconds, and then you can basically then bias or tune all your measurements of Rockoff to this single point. It's accurate, but it's not very scalable if you've got lots of data that you're working through. A second method is to use a Rockoff threshold. So you apply a moving average filter to a sample by sample Rockoff calculation, and then you're basically saying that your Rockoffs are pretty low here, and then as the disturbance starts, then you get a high Rockoff. And you say that the disturbance has occurred when the Rockoff exceeds a certain threshold. So Inui found that 0.04 Hz per second was appropriate in Japan, and in the Nordic system found that 0.035 Hz per second was appropriate. So it's very much dependent on the system size, I'd imagine. A final option is to use detrended fluctuation analysis, DFA, where the frequency trace here is divided into just blocks of time windows. So there's n of them. And in each time window, you're basically getting the trend line. So you're getting each trend line here. And at the point where there's disturbance, you will find that the trace or the root mean squared deviation of the trace from the trend line just gets very large, which kind of seems obvious when you see this particular disturbance, and you deem an event to have occurred or to have started when it breaches a certain threshold. So Ashton has claimed that this is a lot more accurate than the Rockoff threshold. The inertia estimation method that's been described using the swing equation is typically used on historical events where you've collected all the data from a generator contingency or a load tripping or an interconnected trip, and you've put all the data together and you're analyzing the event after the event has happened. But it is desirable for, at least for system operators, to have a real-time estimate of inertia, so that you can monitor and track sort of inertia trends in the system, and just have a level of situational awareness to identify risky scenarios, and also as an input into procuring frequency control services. So maybe you might have in a low inertia state, you might want to procure additional fast frequency responses. There are some examples of online methods. So the most common online method is basically just the summation of generator inertia. So in the SCADA system, you know your breaker status of all your transmission connected synchronous generators, and you generally know their inertia parameters, or you can at least estimate their inertia constant H. So this is like a lower bound inertia estimate and excludes all the generators that are unobservable from SCADA as well as any load inertia. This is sort of fairly standard among system operators. So a couple examples here. This one's from Texas in ERCOT, and this one's in the Nordic system. This is a fin grid picture of it. And also AEMO does this as well as AirGrid. Obviously, the real-time generator inertia monitoring just on SCADA breaker statuses excludes all the load inertia, all the demand side inertia, and inertia from small generators that can't be observed. And so one way to sort of capture a little bit more of that is to augment the generator inertia monitoring with a load inertia estimate. And here, this is what we do in the Swiss, and we basically estimate the load inertia based on linear correlations with system load based on past inertia estimates from historical events. So what we actually found was that there are two sort of correlated blocks, and we tend to choose a more conservative option and use this linear correlation. Second option for online inertia estimation is to use a WAMS-based estimate. So you use strategically placed PMUs to detect and measure disturbances in real time, and then the WAMS can basically estimate both the frequency deviation and any of the active power imbalances, for example, so changes to detector flows, so that you can just plug that straight into the swing equation for inertia estimate. I'm not aware of any real-life systems that actually use a WAMS-based estimate, but they are in the research literature. An alternative approach, it's not really measuring the full system inertia, but it's an idea that is sort of developed by GE. It's called effective area inertia, and it's to calculate the effective inertia bounded by an area. So if you had an area that is is completely bounded by interconnectors, for example, such that you can actually measure the flows across the boundary. So it flows in and out of the boundary, and you can measure all the power within the boundary, so all the generators and all the loads, then technically you can calculate the inertia in across the boundary or in that area. Our final method for online inertia estimation, which is quite an innovative method, is to inject these small but periodic active power perturbations into the system and then measure the corresponding frequency deviations with the PMUs all over the system. And so if you're sort of modulating and injecting a sine wave into the system, then you can basically try and extract that sine wave back through signal processing and measure slight deviations in frequency, and then you can calculate the inertia with the swing equation approach. So this is a method that was patented and commercialized by Reactive Technologies in the GridMetrics product, and then they have undertaken some trials in the UK and Japan.